We now discuss the concept of the demodulator, and we start with that of coherent detector or demodulator of ASK. And we say that this constitutes of a balance modulator followed by an integrator and a decision-making device. So it is like we are repeating the process that we have in the generation of the ASK signal, because we are having another modulator which is now followed by the integrator. So of course we have said that this one is equivalent to the product modulator, which means that we are multiplying the two inputs, and in this case the binary ASK signal and the locally generated carrier signal. So we will see in few steps. So of course this is the diagram. This is now at the received signal. We are talking about when we're talking about the demodulation, just to be clear, is that we are at the source. We have the sound. Someone is talking at some point. The sound is received by a microphone, which produces an analog signal. This analog signal is sampled and demodulated so that it is this is the analog to digital converter. This generates for us binary streams of ones and zeros, and this signal is taken through a pulse encoder, PCM. This gives us a line code, which is the one we are referring to as the unipolar non-return to zero. Unipolar non-return to zero. So once we have the unipolar non-return to zero, this now becomes our binary stream. This is multiplied by the product detector with the carrier signal, the one that we are calling CT, that is locally generated, and therefore we are able now to have an ASK signal. So at the ASK signal, on the other edge or the other side of the receiver, this might be, say, at a radio station that we want to transmit a signal. So it is traversing a long distance. Then at this side, we are receiving an ASK signal. And an ASK signal requires now to be demodulated. So this is the ASK message. This now we are calling demodulator. The demodulator is now the one that is supposed to convert the ASK transmitted signal to become the binary data streams that now can be used to represent the data that was initially transmitted or sent to the modulator. We are saying at this stage we are going to have to be having another local oscillator. Local oscillator simply does what? The local oscillator generates a carrier signal that is similar in frequency to that of the transmitted ASK message. So what happens on that edge is that when we multiply this locally generated carrier signal, we are going to be having two sine waves, which we can now obtain as follows: that we had a transmitted message ST having amplitude of A, and then cos of 2 pi fc of t. And when you multiply with another locally generated signal, say of any amplitude, the most important thing is the cos 2 pi fc of t, where we know that cos A times cos B, this gives us 1 over 2 cos of A plus B into bracket plus cos of A minus B. So when this is now what is called, when we see that this is going to be one, now in this case this is FC, and this is going to be FC. This becomes a double frequency component. So you're going to be having 1 over 2 cos of 4 pi FCT, because previously we had 2 pi FCT. And then the plus cos of 0. So the objective is cos of 0 will give us a 1, but the cos of 2 pi of FC, cos 2 pi FCT will give us a double frequency component. This is unrequired. This is unneeded. So we are going to be taking this through the integrator to kind of cut off this double frequency component, and therefore we are only left with the cos 0. Cos 0 is equivalent to 1. Therefore we are simply left with our original signal amplitude that is divided by 2, and therefore this signal can therefore be taken through the decision making device, so that if the A over 2 is within the decision. Remember, we had something we refer to as the decision variable or the threshold value. So if the A2 that we have is closer to the value for 1, which was root EB, then we are saying that this is detected as a 1. If it is closer to 0, then it is detected at 0. So we have said that the integrator operates on the output of the product modulator for successive bit intervals TB, and this essentially performs low pass filtering action. We are removing the high frequency, which is a twice frequency component that is generated by multiplying the transmitted signal with another locally generated carrier. Then we also say that we make a decision in the favor of step 1 when the threshold value is exceeded, which is now nearing the value, the ideal value of step 1, and if it is less than the threshold value, then it is going to be considered or to be interpreted as having as being as of step 0 that was transmitted. Now we're talking about coherent because coherent means that the local carrier that is generated at the receiver is synchronized with the carrier that produced the signal, or that produced the original carrier signal. So that is exactly what coherent detection means. That it means that there is perfect synchronization of the carrier signal used in the ASK modulator on the transmitter side. So what exactly I said, if this is our transmitter, and this is our receiver, this is TX, this is RX, and here we are talking about a carrier. We are talking about, this is our product modulator. I think that is how we are drawing. This is our product modulator. This is our incoming bits, or the encoded signal. This is the unipolar non-turn to 0 encoded bit stream, and here is the local oscillator. So this local oscillator requires to be synchronized with the local oscillator that is going to be multiplied with the received ASK signal here. So there is perfect synchronization that the local oscillator here that is generating the cosine of 2 pi fc is perfectly synchronized, and this means that the phase, both the phase and the frequency fc that are generated at this local oscillator are in perfect synchronism, or that they are matching. When we are, if the signal is going up, which is now let's say the signal is going up on this side, the same signal is going up on this side. Therefore, those two are in that is what it means to be in synchronism. But there are two now forms of synchronization. One is the one that aims at synchronizing the phase, and the other one is the one that aims at synchronizing the frequency or the time. So the one that attempts to synchronize the phase, it ensures that the signal generated locally in the ASK, the modulator, is locked in phase with respect to the one that is used in the ASK. So just as I have said here, that when the signal is going up at time t, the signal here is also going up. This is at the TX and this is at RX. The signal is expected to be in phase. When they are in phase, that means that when one portion of this signal is going up, this other portion of the signal is going up at the same time instant. So at time t1 and at time t1, the signal is actually having the same phase. That is the objective of the phase synchronization. But the one of time synchronization, this one aims at timing the decision-making device in the ASK demodulator with respect to the switching instant. At the intervals when you are here on the transmitter side, we are generating the pulses. So on the other side, which is at the receiver, here we are sampling the signal. For instance, we are receiving this kind of a signal. So when we are sampling, that means that when we sample at this point, it should find a 1 was transmitted here. At the same time, one was transmitted there. If at the second timing instant, it samples and realizes that there is no amplitude, it is a 0, that means that here what was transmitted was a 0. And on the other hand, if we timed here and we found that we have received a 1, or the value that is received, it is within the range, or it is beyond or bigger than the threshold value, then it will translate that as a 1. Therefore, here we had a 1 transmitted, then as 101, and here we have received 101. But in the event that we have mismatched instance, I want to use a different color. We have mismatched instance. Probably at this point, the time at which we are switching our demodulator to to detect the signal. It might be late probably with some time tau. If tau is in the range or is bigger than probably half of the period TB, that means there are times when we might realize that we have sampled a zero whereas one was translated. And then we might have sampled again at this time and still receive a zero because there is some delay that is causing us to have unsynchronized demodulation. So what we are simply saying is that the objective of the timing synchronization is to enable proper timing. So I'm not saying that this is necessarily the parameter that we set to make sure that there is no unsynchronism or in synchronism. What I'm simply saying is that we must make sure that the switching instance are matching with the time in which the bait interval is on the transmitting side.